Good. First of all, welcome to the first development conference from Lattice in 2023. And I would like to talk about solution stacks in Lattice, special on the Automate solution stack. I'm Karl Wachsmann from Lattice, Principal System Architect, but I will come later to my intro slide. I have with me Roland Neumüller and Balthasar Wagenhuber. And I would like to introduce myself first, and then I will hand it over to the El Camino guys. So I'm a principal system architect focusing on industrial topics in Lattice. Have a little bit of history. I'm getting old. I'm more than 30 years in this business. On the industrial side, have a history on Intel in 2021. Joined Lattice and leading the worldwide principal system architect position in Lattice. And I would like to hand it over to Roland.
Hello, everyone. Let me introduce myself. My name is Roland Neumüller. I'm the CEO and one of the founding partners of the El Camino GmbH. So we are design house, electronics design house based out of Germany. And we have a team of more than 20 highly qualified FPGA and ASIC engineers in our company. And I myself, I'm responsible for sales and business development in all commercial aspects at El Camino. Since 2020, we have a very strong partnership with Lattice Semiconductor. And in fact, related to this presentation today, we have a dedicated team developing and supporting industrial Ethernet for Lattice. And just to give you some background, also in the semiconductor industry, quite some time, almost 30 years, at various roles at Altera and Cypress Semiconductor, from applications, field applications engineering to sales and account management for some of the bigger customers. And since 2019, I'm the CEO of El Camino. And I just would like to take the opportunity to thank Lattice very much that we as El Camino can be part of this great Lattice Developers Conference 2023. Thank you.
Thank you, Roland. I may introduce myself. My name is Balthasar Wagenhuber. I'm a senior solutions architect at El Camino. As a hardware engineer, I have accumulated over 30 years of experience in industrial design. Before joining El Camino, I provided support for various semiconductor companies to their distribution partners and customers, with a focus on new product introductions, design-in and field application topics. In my previous role as a field applications and technical sales engineer for a semiconductor representative, I have gained extensive experience in addressing customers' technical challenges and helping with technical issues. Thank you very much, and back to you, Karl.
Thank you, Balthasar. So, short to the agenda, I would like to start with a little bit overview on the IoT or the IoT, industrial IoT needs and challenges. Then a little bit architecture discussion about Industry 4.0 versus 3.0. Then trends in the connectivity, security, and AI topics in the industrial world. After this, I would like to give you an overview what we can do in the solution stack and map all the challenges and needs into the solution stacks. Then I will hand it over to the El Camino guys, and they will give us an overview of what they are doing. And at last, I will give you AI solutions, what we have from other partners, for example, EXO International, and then I will sum it up. So let's jump into the topic. So needs and challenges. So if you look to this page, and I think in the last 2-3 years, every country or every area have the same goal to reduce energy consumption or make it the energy efficiency higher and reduce the CO2 emission. So you see on this slide a lot of quotes from big companies like Siemens, ABB, GE in different areas. On the motion side, Asia Pacific is growing on the motion or the electric motor market, more than 40% market share there. So we see also in the middle from Siemens a quote from Portugal that we need a higher efficient motor. So this IE3 is an IEC standard means that's an efficiency, and we need a better efficiency. We should move to 4, and if the number goes up, the efficiency goes up, only for clarity. And if you look on the energy side, also the distribution from energy, this DRMS is needed to control the energy what we need in different sectors, that we include the renewable energy into this concept. And if we sum it up, all the quotes needs connectivity, needs special implementation that the customer can, first of all, get it done more efficient, and can also simulate or make some special implementation that can control the new implementations. If we split this up, what I said, it is the industrial trends, and I split this in 3 sections there. One is connectivity, and this is since more than 20 years a topic about industrial networks. And you see in the top there, I'll use my pointer, the old or the standards what we use today from EtherCAT over Profinet, Ethernet IP. So you see in the industrial world the communication over these Ethernet protocols. In the future, or a lot of customers are now investing in an OPC TSN implementation, and you see also the who is who from customers on this picture. You find also the link on the Wikipedia where you can find the information. I would like to jump then on the right-hand side. That is also a dominant as a driver in the market. Government regulatories, or sorry, stop. This is also a driver in the market, government regulations. So I said before, ISC4, the ISC5, Europe and the US market or government gives new rules to the customers and to the factories that they need to use IE4 motors. So it means new motors with higher efficiency, and you need a better implementation, perfect for FPGAs. Second, we have a trend on the security side. The security needs higher level root of trust, and the European Union and also US are defining new standards there. And safety, clear, everybody should be safe in this environment. If a motor is turning, you should have a safe environment, and the whole motor should stop if anything happens. In the middle is the combination out of the communication or the connectivity and the rules. We try to make a virtual workload in the cloud to have virtual PLCs, and this drives real-time deterministic or decentralized control in the field. So this means you have remote IOs, they have some real-time functions on it, and what is not real-time moves into the cloud. And with this, we have a more efficient implementation. But this is also a perfect play for our WAN devices. They can handle this real-time workloads very easily, and can also include some AI functions or other functions. So this said, I would like to jump more or less in this overview slide, Industry 3.0 and 4.0. And the main difference is 3.0 had the control path of a factory defined, how control loops, latencies, deterministic implementation was everything defined there. And this moves now to the Industry 4.0. We have now cyber physical systems, we have Internet of Things, and we have bigger network. We are coming to the point to combine IT, the infrastructure technology in offices, with the OT world, the factory, the operation technology, to get there more data from A to B, that we can handle the processes better. You find this also in the standard manufacturing words like smart factory or smart manufacturing, cloud computing. You see IoT, the IoT for industrial IoT, Internet of Things, and IoT, industrial Internet of Things, more or less are also used in this environment. The main focus, and it's in the last line, is the latency of the data, what I said before on the connectivity side. As in the new concept, not only the control data get more or less analyzed, it's also the inside data, camera data, or measurements, what you can do in the system. And with this, you get AI functions included. And last but not least is this the data security. You uncover more data, and with this data, you make some prediction or some improvements, and you would like to handle this data in a secure way that you own the data and you can secure the whole process. So that is more or less the trend what we are seeing, and we see also some new names like in Industry 5.0, more on the AI side, but we will see it a little bit later. Good. This said, I would like to show you this in a diagram of an ISO 95 model. You have on the left-hand side the levels of the model from level 5 to level 0. And you see in this diagram, it's more or less a control loop time definition. Layer 0, you're going down into microseconds, very deterministic implementation. You are in the sensor level, and the sensor level gives you a requirement that you have some updates, some inputs that you should control, and the control loop in this 100 microseconds area. On the layer 1, layer 2, layer 3, the control loop time is more relaxed. You have in layer 3, for example, 100 milliseconds to 100 seconds. The second point, what everybody is interested in, on the power consumption. If you have a motor and it consumes 50 watts to get it up and running from the controller side, it's not efficient. So in this layer 0, layer 1, you should have a power estimate below 4 watt or below 0.5. And if you look to this, that is then mapped into the solution. You see there that FPGA, and the FPGA is dominating layer 0 and layer 1 because low power, what you can offer from Lattice, deterministic implementation, low latency, real-time communication. And if you go up, you see more and more CPUs are coming in, and our partner NVIDIA is also there, and ARM and RISC-V are making more and more workloads in the upper layers, layer 2, layer 3, layer 5. And to give you some examples, I put the numbers is 1, 2, 3, and I would like to jump into this. I can give you some examples what we are doing in this area. So on the next slide, you see in the top the 1, 2, 3 again, and I would like to guide you through this slide. So we have on the one left-hand side, the point there is the industrial edge AI. Everybody is talking about this. You have a machine, cameras in the top that streams the data in, goes over the frame grabber card. The frame grabber card can accelerate or give the data in real time to the CPU in the back. There are NVIDIA, a processor, and there is the AI or the analytics behind. This CPU gives then the information back, goes into the control line, and can then select the right product, or say the quality is not good enough, or. So this means on the CPU side, you have the control system, you have the AI machine learning up and running. And on the FPGA, as I said, connectivity, deterministic, and full-send security. And you have also examples there. They're using concepts what we have shared with them, maybe not with NVIDIA, maybe they use some other CPUs, but the concepts looks always similar. In the layer 3, 4 area, we have the workload consolidation. This was pointed with 2. We have some OT worlds. They are connected to the IT world. This means the crossover between the operation technology to the information technology. And this FPGA can bridge the gap and can also make some pre-calculation like virtual soft control systems like virtual PLCs or the multi-control functions, and the values on the FPGA side stays the same. It is more or less implementation from system integrators. They're building this up, they're giving this to customers. And last but not least, if you go up in the layers, we have this Industry 4.0 and 5.0, what I said before. And the focus is there to make analytics, digital twins from the factory, and you have their complete systems, complete factory in this environment. And NVIDIA can make the calculation there. And what we can bring is, again, the connectivity to the OT world, the latency on the calculation, and also security and FUSA on the safety side. We are working very aligned with BMW today, and you see this also in the keynote speech, what you have seen on the December 5th, where we had Mr. Hasselbeck there, and he have shared more of the challenges, also the needs. I would like to double click a little bit on the security, that I give you a little bit insight on the security, what is going on. It's the security trend in Europe. It's the European Cyber Resilient. And we'll come back later to this point because we have also a solution for this. So what the European Union have defined is a cyber security implementation from start to end, from planning, design, development down to the end of life phase. So the whole maintenance is included. You have the documentation in, very defined. You go in the complete implementation with a clear documentation with the risks and make the analysis per device. If you look it through, it is really a implementation that you get a complete security solution from the OT vendors like Siemens and others, and can make the implementation in the right way. The tricky stuff, what we are seeing, that the customer should maintain this the next 5 years if they release it. So this means they don't know which security features they need in 5 years. They don't know which challenges they get, but they should guarantee at least 5 years to get it up and running. And we see in the industrial world, this FPGA plays a very important role there. On the right-hand side, I copied in more or less this three different types of the Cyber Resilient Act. This default, you see there, you make your self-assessment there, and that's more or less the equipment what you have there, or examples. If we look to this IoT world, what I have described before, you have microcontrollers in. So this means self-assessment is not really possible there. You should go to TÜV or the other certification bodies. They make an assessment of your implementation, of your needs, with the standards like IEC 62443 and others. And the class 2, all the CPUs, all this layer 2, layer 3 products, what you have needs the certification too, and you see it goes up and up and up on the needs. You have their operation systems and also CPUs. You need there also the root of trust. As I said before, we're working also on the security side with BMW on the InnoHub in Germany, and build up their end-to-end security. And you will see next year more about this. We will definitely release this in different white papers and also presentations. So now I'm jumping back to the solution play. So what is our automate stack solution or automate solution stack addressing? So what we would like to do is, or what we are giving to you is an acceleration tool to accelerate your development in areas like robotic, multi-channel motor controls, give tips and tricks on the predictive maintenance implementation, and real-time industrial networking is also a big part in this solution. If we look this into this Lattice implementation style, we have on the lowest level the hardware. So we are building different eval boards that you can use and buy. from your distribution channel or from the web, and all the different cards have a special function. This middle card, Certus NX, is a card with a low power or a very efficient implementation of FPGA with a very low power consumption FPGA, and we are controlling their drives. This on the left hand side, Certus Pro is the big brother from the Certus device, and that's our main device. This device runs the RISC-V FreeRTOS implementation with the Ethernet connectivity to the node system, to the motors. The motors can give the predictive maintenance data collected to the main node system, what you have on the left-hand side, and you make the CLC connections. You see everything is connected, and you move the workloads to the right position, what you would like to have, near to the motor, near to the main system. After the IP course, we have the implementation tools in the next level. We have the RISC-V with the hardware acceleration of the AI function, and we include also the OPC-UA foundation stacks like OPC-UA PubSub. We're working on the OPC-UA FX implementation and MQTT. Out of the 3 lines of the levels, we're building then a reference design, what you have written there, from real-time industrial network OS with FreeRTOS down to multi-access motor controllers. And then we have the different implementation. We can help with customer design services to help you on this. This said, FPGAs are very important in this world, and our FPGAs are mapping very aligned with the needs or the industrial needs. This means lower power by 75% as if you compare to our competition with the same logic size, with the same speed. If it's needed, we can fit in very small areas. We have devices below 3 by 3 millimeters. We have the security features in for zero trust security. We have the performance with the low power devices to handle gigabit transceivers or 10 gigabit transceivers. We have reduced the single element upset to have a better implementation or a higher safety implementation on the device. And last but not least, I think that's a must-have if you play in the industrial market. It's the lifetime minimum, 50 years, and we have all the devices, and yeah, that's just the implementation that we have. Good. Last but not least, I would like to share this OPC-UA TSN topic. So we started last year on a partnership with the partners, what you see in the lower area in white, from Analog Device to Texas Instrument, Schneider Electronics, and P&R, or a group out of EBB. The whole partnership is led by AWS, and the goal is to have a field device with OPC-UA on TSN. And this is the moment what I would like to hand it over to El Camino, because they are working on these topics or multiple Ethernet topics, and they can give you a short overview on the activities what they have on the plate. So, Roland.
Yeah, thanks, Carl. Yeah, let's go to the next slide. Yeah, let me just give you a brief overview about El Camino, who we are, what we do, how we can help you as a Lattice customer. So we consider ourselves a design house for programmable logic and functional verification. So programmable logic, obviously FPGAs. Functional verification is more on the ASIC integrated circuit side. El Camino was founded in 1999. 2 of the founders was Wolfgang Löber, my CTO colleague, and myself, and we are managing the company right now, and we are also the owners of the GmbH. We have more than 20 highly qualified FPGA and ASIC engineers in our company, and we are located south of Germany in the beautiful Bavaria, small town called Mainburg. And our expertise is in everything related to FPGA, so let it be FPGA design, consulting, training. We can optimize your design for fast performance, low power, or a small area. We build custom FPGA boards with PCB design and manufacturing, and we can build custom IPs and integrate these IPs in bigger designs. And the second area, as I said before, is this ASIC chip verification. We call this UVM. So this is where we mainly focus on universal verification methodology, which is a standardized methodology for verifying integrated circuit designs. And we're using languages E and System Verilog for this. And now let me talk specifically about Lattice, what we do with Lattice. So we have a strong partnership since more than 3 years now. And so we can do, for you as a Lattice customer, we can do complete turnkey designs, partial designs, can do conversions from other FPGA vendors to Lattice, can consult you, can support you, can provide training. And specifically on the topic today in this presentation, we have a dedicated team for Lattice Industrial Ethernet. So some guys in our company, they don't do anything else than Lattice Industrial Ethernet. And they can help you with a kickstart of a new design if you are new to the topic. We can support the implementation and integration of the various industrial Ethernet protocols. Together with Lattice, we do demo and reference designs, and this team can also provide applications support for you as a customer. We are also EtherCAT Technology Group, ETG, member as El Camino. Now we will go more in the technical details, and for this, I would like to pass on to Balthasar.
Thank you, Roland. Now I will present some slides that show the Ethernet protocol details and how Lattice semiconductor tools and boards enable a quick evaluation of industrial Ethernet solutions. So industrial Ethernet, in simple terms, is an industrial data transmission system that utilizes the IEEE Ethernet frame data structure and operates with the IEEE approved physical layer interface. For instance, it may be used to exchange process data between a PLC unit and distributed IOs or an external motor control unit. For Ethernet, but Ethernet can also facilitate the exchange of higher level data with industrial devices, including data for configuration, diagnostics, and maintenance, typically using the IP protocol layer. Carl, maybe you can point on the bottom of my slide on the Ethernet frame for my next explanation.
Okay.
Yeah, this slide here illustrates a fundamental concept of the Ethernet protocol on the bottom of my slide here. The basic structure of the Ethernet frame is unchanged since the early 80s. Preamble patterns and the start of frame delimiter pattern are indicating a subsequent Ethernet frame. Starting with the 48-bit MAC address or the addresses of the communication partners, destination and source addresses are marked in blue here on my slide, followed by an Ether type field. Then the MAC client data is transferred. This section is marked in yellow and contains the data according to the upper layer protocols. At the end, a correct frame checksum, here marked in blue, indicates a frame with no bit errors and enables or ensures error-free data transmission. The EtherCAT field, please point on the orange fields here, please. The Ether type field highlighted in orange is key. It effectively acts as a protocol identifier, indicating which higher level protocol is encapsulated on the data portion of the Ethernet frame. Type values are unique and are assigned by the IEEE. An Ethernet device that is addressed by the destination MAC is first checking the Ether type value. If it is known and supported protocol, the frame is received and processed on the higher level. If it is an unknown Ether type, the frame is discarded. I have added a few examples of the Ether type field used for industrial field bus communication. First, okay, 88A4 identifies a frame with field bus data for EtherCAT, defined by Beckhoff in Germany. This upper layer protocol includes a EtherCAT header, the orange field here, or the red field, and one or more EtherCAT datagrams. Both the header and the datagrams have to be processed according to the EtherCAT specification. EtherCAT is using this protocol layer for real-time process data, configuration, and diagnostics. Next example is 8892. Okay, thank you. This identifies a frame with field bus data for Profinet. Profinet has been defined by the Profibus and Profinet International Group. This upper layer protocol includes a frame ID, real-time I/O data, a cycle count, and a status field. All of these parts have to be processed according to the Profinet specification. Profinet is using this protocol layer only for real-time process data. For configuration and diagnostics, Profinet is using higher level protocols, based on IP4. Carl, you can point on the last example here for my further explanations. CC-Link, for example, is using only IP protocols and its mandatory services for real-time data and configuration. Mandatory services for the IP communication are the 88CC. It identifies the link layer discovery protocol defined by the IEEE. It allows network devices to advertise their identity and capabilities to other devices on the same network. Profinet may use this protocol for network diagnostics and topology checking. Next one is 0806. It identifies the address resolution protocol defined by the Internet Engineering Task Force. Its purpose is to map an IP address to a physical MAC address on the same network and is mandatory for IP4 layer communication, used to discover the MAC address associated with a specific IP address. The ether type value of IP4 communication itself is 0800. It identifies the Internet protocol defined by the Internet Engineering Task Force as well. All well-known Internet services are encapsulated here. For example, UDP or TCP/IP. Profinet is using this protocol layer for network configuration and diagnostics features. So next slide then, Carl, please. Thank you. For industrial communication, a golden system reference design with MCU core and Ethernet connectivity is available in the Propel Builder tool from Lattice Semiconductor. Propel Builder is an easy-to-use system IP integration environment and a key tool to quickly build processor-based systems. MCUs and other IP components can be easily integrated, configured, and automatically interconnected with memory resources and peripheral components. This reference design is a pre-configured solution for Ethernet communication. If you look at the block diagram, with the IP components such as RISC-V MCU or a triple MAC Ethernet MAC controller IP, access to internal system memory, a memory controller IP to enable the access to an external DDR4 RAM on the FPGA board, or various other peripheral components for general purpose topics. This reference design is ready to build industrial Ethernet solutions using standard IP Internet protocols, as mentioned before, UDP, for example, TCP/IP or higher protocols, or field bus standards directly based on Ethernet layer 2 and identified by a specific ether type value, as explained on my first slide. The Propel SDK software development kit supports a bare metal or FreeRTOS-based software development. The golden image principle enables fail-safe firmware updates over Ethernet. Thank you. Next slide, please. Let's have a look at the hardware available for solutions based on the Golden System reference design. The FPGA board with 100 meg, 1 gig, and 10 gig Ethernet ports is available for a quick evaluation or a rapid prototyping of industrial Ethernet solutions based on the Lattice Certus Pro NX platform. Thank you. Next slide, please. My final slide summarizes the key points from the previous technical slides about Ethernet standards, the reference design, and the evaluation hardware. These components now come together to create a demonstration setup. For the adoption of industrial Ethernet protocols, My final slide summarizes the key points from the previous technical slides about Ethernet standards, the reference design, and the evaluation hardware. These components now come together to create a demonstration setup for the adoption of industrial Ethernet protocols on the Nexus Pro NX family based on the Versa evaluation board. This setup is perfect to showcase and explain the features, capabilities, and functionality of various industrial Ethernet protocols such as Profinet, CC-Link, or others. A Windows 11 PC with various software components is used for development, implementation, configuration, and testing. Mandatory tools for the implementation of the reference design are marked in green on my list. The Lattice Propel System Builder, the Lattice Propel Software Development Kit for setting up the appropriate software stack and the development of the slave applications. The Radiant FPGA design software for design entry, synthesis, place and route, bitstream generation, and programming. A Wireshark tool enables the capturing of frames on the Ethernet port to analyze the raw data and field bus protocols. A master device simulator running on a virtual machine on the PC enables the network configuration and testing with no connected programmable logic device. The shining Golden System reference design box in the middle of my slide refers to the pre-configured MCU solution within the FPGA logic. The bigger picture on the slide shows the complete architecture of the reference design solution on the evaluation board. The green box contains all hardware and software components on the printed circuit board. Components marked in orange are hardware resources on the FPGA, for example, internal memory. Yellow boxes indicate logic IPs defined within the reference design. A triple-speed Ethernet MAC IP core and a RISC-V MCU core are implemented here as mandatory components for Ethernet connectivity. External active components on the board are marked in red, for example, external DRAM or flash memory, or the Ethernet PHY on the external transceiver module. Connector plugs are shown and described in gray boxes. Blue boxes stand for software components running on internal or external memory, depending on memory size requirements. RT Labs is a software partner of Lattice Semiconductor for industrial Ethernet software stacks solutions like Profinet or CC-Link. And El Camino is collaborating with RT Labs on the hardware-software interface and is responsible for the FPGA logic and IP integration. Standard Ethernet frames are exchanged on the data lines on the bottom of my slide between the master device simulated on the PC and the slave device implemented on the evaluation board. The blue lines represent the way out of the master sent from the master device to the slave. The red lines signify the response frame sent from the slave device back to the master device. Thank you. Now back to you, Carl.
Thank you, Balthasar. So a little bit on the roadmap, what we are working on, multi-industrial Ethernet support. So we would like to get the IPs from the different partners. You know, Beckhoff is leading the EtherCAT topics. On the Profinet side, we're working, as Balthasar said, with RT Labs on a software stack, and we're using our IPs. TSN with CC-Link is a partnership between CAST, as one TSN partner, and also RT Labs and El Camino. And TSN OPC-UA is a implementation, but we are looking internal, and we're working also with El Camino together. The whole hardware platform is a Certus Pro NX device, what you have seen before in the picture with the golden hardware reference design, what we have released on December 5th. And this golden hardware reference design is a part of the Automate stack. As software partner, mentioned before, RT Labs is our main software partner in this area. If we look now a little bit deeper into our other application, we're working there with EXA International together. This is a HMI implementation, and you see in the top there IT communication to the cloud. There are different cloud systems and also protocol systems. There are MQTT or OPC-UA. And there is the connectivity down to the OT world, motors or sensors over EtherCAT, CAN, OPC-UA. This device in the middle should be the bridge, should show the data, should communicate or have the connection to the cloud to get the data in. And this software is running in this Corvina cloud from EXO International. Downstairs, this is more or less a side picture from the side, from the top down, from the HMI, and you see all the connectivities there, all the connections. On the next slide, we split it up, not only IT OT, more into the left-hand side non-real-time, right-hand side real-time communication. So this Corvina implementation in the cloud or on the CPU handles all the connectivity domains with a controller, have the security and also the management of the whole cloud and software management. So this means this runs on a CPU, ARM CPU. On the Linux, we have the control as a service, motion as a service, or a function for an HMI as a service, or field buses and the I as a service. So a standard new IT implementation. To connect with the older world, with the OT world, to get the sensors, IOs, motors, camera interfaces in, we need the real-time topic. And if you remember to this NVIDIA slide, what I had 1, 2, 3, we have there the same values: real-time domain, control loop definition, the last mile connection with different protocols to the sensors. This is used in areas where you need servo motors or some multi-sensor controllers like AMR. This said, you will see on the next picture the module what we have with additional features, but this module is available from Exor and have the complete applications up and running. You see it there on the top on the right-hand side. That is the complete implementation. There is the Lattice FPGA, there is the CPU, and then you have a lot of memory. And by the way, that's a €2 a coin what I put nearby, that you see the dimension of the board. So what we have on the board, and you see this in the block diagram, is the CPU, makes the housekeeping function, makes communication to the cloud. On the right-hand side, the communication. There is a ECB5, for example. The same what Balthasar shared before. All the kinds of protocols are supported there from the main node side. And there is in the middle a new device. That's our security device, a Marixo 3D, handling the security topics. And this is shown on the left-hand side. So this is the first IoT solution with this IoT chip, that is the ECB5, plus Ethernet, industrial Ethernet, and security. So what we have done, we added a platform firmware resilient implementation aligned with the NIST standard, what you see there. This gives us a scalable solution. So we have a root of trust in the middle of the system and have in real time, in nanoseconds, a firmware check. We can detect any updates or downloads and have there the root of trust in this device. They are not able to bypass the whole stuff because we are the first device on the board that powers up, and the whole power sequence is controlled by this MARIXO device. And with this, we are achieving a higher security as only root of trust. We are the first device to control everything and the last device that gets from the power rail down. With this, we achieve 3 levels on security. Protection, clear. We would like to protect our system that we get no risk or no hack in the system. But over time, it could happen, and that is aligned with the Cyber Resilient Act from the European Union, because if we get an attack and we have not really the right tools to stop this, we can detect this in real time. So the FPGA is root of trust, see access, and say, okay, that is not a normal access. That is something wrong. I should protect my hardware, my software, my memory. And with this, the detection reacts then, or the gives models the token over to the recovery side, and then we came up with a new image, with a golden image, or we stop the whole communication and say, okay, we have a problem, we have a security risk, we are not communicating anymore. You see, it starts with communication, real-time communication. On the implementation, you have also the security device, and with this we can go after the Cyber Resilient Act in the European Union. So this said, coming to my last or my summary slide, we can address the needs what we see in the industrial world on the Industry 3.0. We can make the communication, the older standards like EtherCAT, Profinet, CC-Link very soon. So we try to get everything up and running with the El Camino implementation. We can make the deterministic control, and we can also make the motor control. You have this in this automate stack available. You can make a download, you can make implementation. If you would like to use some 4.0 implementation like predictive maintenance, AI, the systems are there. Decentralized control is available on the platform, and also the cloud to sensor IEEE or TSN communication with OPC-UA and 3 others is available. And very soon we get the complete end-to-end solution. End of this year we have a new release of Automate Stack where you can make an end-to-end OPC-UA communication from the last senders up to the cloud. This said, I would like to thank you first of all that you spent the time with us. And second, maybe you have some other questions and we can give you some answers.
Thank you also from our side.
Thank you.